Welcome back. My name is Clayton, and this video is just going to cover the quiz questions, the practice problems from the hybridization quiz. So let's jump right into it. Question 1, if two p orbitals and one s orbital are hybridized, this will result in, and then we have to choose the correct answers. So we have, I'm just going to write the general here, s, p, 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 because we know we have three orbitals in the p sublevel. So this says two p orbitals and one s orbital are combined. So that is going to combine these. So conservation of orbitals tells us if I combine three orbitals, I'm going to create three new orbitals. So I already know, first of all, I'm going to get three new orbitals out of this. And what are their names? Well, I combined an S, a P, and a P. SPP, also known as SP2. So I'm going to get three new SP2 hybridized orbitals. All right, question 2. Which of the following hybridizations follow conservation of orbitals? All right, so once again, we know that three orbitals in equals three orbitals out, right? So on mine, I have S plus P yields SP2 plus SP2. All right, so we got this half correct. These three, when we combine them, they do in fact make SP2 hybrid orbitals, but the problem is we need three of them. So this one does not follow conservation of orbitals. Let's look at the next one. S plus P plus P plus P. Okay, so I would expect sp3 hybrid orbitals, and in fact, we do get that from the prompt here, and we get that times 4. I put in 1, 2, 3, 4, and I got out 4 sp3 hybrid orbitals. That one does. All right, next one down. S plus P yields sp plus sp. All right, I put in 2, I got out 2. That's conservation of orbitals, and they are the correct names as well. I combine an S and a P, I get sp hybrid orbitals. Very good. And the last one, S plus P yields sp. We know this is incorrect because we can't combine two orbitals and only get one. We need another one over here. So although the name is correct, it does not conserve orbitals. So these two are the correct answers for number 2. Number 3, hybrid orbitals. Hybrid orbitals can hold electrons in lone pairs and sigma bonds. That's it. Fun fact, so make sure you learn it. Hybrid orbitals do not form pi bonds. Pi bonds are formed from overlap of p orbitals in a parallel orientation, which that you will get into in your OChem class. So you don't really need to know that right now. You're going to learn that. All right, question number 4. Identify the hybridization, if applicable, of the following atoms within the compound shown. So let me just draw this real quick. Okay, so when I'm looking at hybridization, I'm looking at the regions of electron density here. So here, for our oxygen, I have 1, 2, 3, 4 regions of electron density. S, P, P, P. That combines to give me sp3 hybrid orbitals. So let me just make that maybe a little more clear here. We have an s orbital and we have 3 p orbitals. So if I have 1, 2, 3, 4 regions of electron density, I'm combining all of those. When you combine them, you get sp3. So that's why I did that up here, spp. All right, so oxygen is sp3 hybridized. The next one, carbon. Carbon has 1 region of electron density, 2 regions of electron density. All 3 of those bonds are in the same region of electron density. If I pull this carbon out, the first bond that forms that is a sigma bond. The next two bonds that form, those are pi bonds. And we know pi bonds are formed from overlap of p orbitals, not from hybrid orbitals. So the hybridization is only for this sigma bond right there and this sigma bond, these two regions of electron density. And so sp and sp, and then I have two leftover p orbitals for those two pi bonds. So the carbon is going to be sp hybridized. Hydrogen is next. So hydrogen, its electronic structure looks like that. It doesn't have a p orbital. It's in the first energy level. You can't hybridize if you don't even have a p orbital to mix anything with, right? So this has no hybridization. So I don't know what the options are. Okay, so I just put S. So it's not Na. It is not hybridized, but it is just an S orbital. That's what it is. Yeah, so if applicable. It is not applicable because there's no hybridization. And finally, the nitrogen. This is going to look real familiar. We have one region of electron density there, another region right there. So that's going to be out of our SPPP, these two regions hybridized. The other two went into the pi bonds. So the nitrogen is sp hybridized. Alrighty. Okay, number 5. In the compound shown, identify the orbitals that are overlapping to form each bond. All right, so to identify the orbitals that are overlapping, what we're looking at is the hybridization and the kind of bond. So the hybridization of the two atoms involved and the kind of bond that we're referring to, sigma or a pi bond. And so if we're talking about the oxygen, we know the oxygen is sp3 hybridized. And so I would say, or we're talking about the oxygen-hydrogen bond first, okay? And the hydrogen is not hybridized at all. It's in an s orbital. So I know that an sp3 is overlapping with an s orbital to form the OH bond. Letter B, we're talking about the oxygen and the carbon. So the oxygen, its hybridization didn't change. It's still sp3. So I have an sp3. The carbon we know is sp. So this brings in information from the last question, basically. So we have sp3 overlapping with sp for the oxygen and carbon. Next one, letter C here. We're talking about carbon and nitrogen. So the first half of it is to form the sigma bonds. So the carbon we know is sp. The nitrogen is also sp. So the sigma bond is formed from an sp-sp overlap. But then we have two pi bonds. Pi bonds are formed from p orbital overlap. So the pi bonds must have been formed from a p orbital overlapping with another p orbital. And that happened twice, so we got two of our bonds. All right, so yeah, no reason to complicate this stuff, right? If oxygen is sp3 hybridized, it has 4 sp3 hybrid orbitals. Those must be overlapping with the orbital of the other thing to form whatever bonds, right? Okay, that will do it. Again, my name is Clayton. Thank you for tuning in. Let's keep an eye out for the next one. See ya.